Okay, please wind conversations down. 10 seconds, all right. We finally have a little room to breathe, and I realize it's the day after the exam, so probably nobody feels like learning right now. We are going to get to technical material in this lecture, but we are going to start off talking about the robot project a little bit, because hopefully we're getting close enough for people to get excited about that. So, team formation. These projects are done in groups of 3, and probably early next week, maybe ideally on Monday, a spreadsheet will go up for forming teams, so we have the teams finalized before spring break, and then you can start the project immediately upon returning from spring break. This is something where there is no way to make everybody in the class happy. A lot of you are junior mechies who know each other, so there's usually a good chunk of people who want to work with their friends. We have seniors and people from other departments mixed in, so there are people who think teams should just be assigned randomly to keep it fair. There are things like research from the physics department showing that if you have groups of 3 with 2 men and 1 woman on a team, the woman kind of tends to get sidelined, even if it's not overt and intentional. Things like, oh, girls have better handwriting, you should do the data sheet, right? How many of you have had that happen to you this semester? Okay, that's my point. So guys, again, going back to like the course evaluations thing, don't be jerks. Even if you're not being intentional about it, be careful about the subtle things like that. So there are people who algorithmically assign teams to either avoid situations like that or distribute people based on GPA to kind of even the teams out. I know somebody who did that one year and then had a female student get really angry and say to the instructor, like, this is infantilizing, I don't want special treatment because I'm a woman, you should just let us pick the teams or do it randomly. So again, people are going to have a huge variety of opinions. There is no way to keep everyone happy. But given that, I am curious what the distribution of opinions is like in this class, or if this has changed since the last time I taught. So I'm just going to activate a poll on it. There's no right answer here. But the options in this poll are either let us pick, assign randomly, assign algorithmically, or again, that could be based on some combination of, GPA, gender, diversity, status, or classes you've taken, what major you're in. So, there's a bunch of different subsets to that, but point being, not random. Or other, if there's some other system. I think those are kind of the 3 major systems. All right, I will leave this poll open for a second for those of you coming in late. A note on that, it seems like the number of people coming in late has gradually ticked up throughout the semester. So I know this is like a huge campus and some of you have classes farther away. Getting to the basement of this building can be a pain. But I've definitely had an uptick in the number of people coming up to me after lecture saying, hey, I wasn't here for the first poll everywhere, and then I have to sort all that out after. So try to renew your efforts to get here on time so we can actually start at 11:15 and I don't have to wait 5 minutes in to launch the first poll everywhere. That just makes my life a little easier. Okay, we are at 77 replies. Again, I know some people just got here and attendance looks a little light today, maybe because people needed a break after the prelim, which we'll also talk about in a minute. But I'll leave that open for another 30 seconds for you to think about it. Again, if you just got here and you missed my initial pitch, we are going to be signing up for teams for the project next week, and people have different opinions on this, so there's no way to keep everybody happy. I'll announce the system we're probably going to use in a second, but I want to see the results of this poll first. So, I'll tell you what, I'm just going to switch over to the responses so I can see them, but I won't deactivate this yet. Okay, so that is actually a pretty overwhelming let us pick. 90% voted for let us pick, with kind of a distribution of assign randomly or assign algorithmically, each getting a few percent. So here is what I have found is the least of all evils trying to keep everybody happy in the past is I do let you sign up, but if, say, you have a group of 2 and you're looking for a 3rd person, or you're just solo and you're willing to join a team, you can just make a public ed post and say, hey, we have 2 people, we're looking for a 3rd person, or hey, I'm looking to join a team. If you're shy about it and you would rather be assigned to a team, that's fine. You can make a private ed post just saying, I would like to be assigned to a team, and the course staff will compile those and just assign teams from the people who want to be assigned. That process is private, so there's no like pick class and gym class feeling to it. So again, it's not ideal or optimal, but I think that has made that process run pretty smoothly in the past. Big caveat on that, again, especially for the junior mechies who already have your group of 3 in mind. So for the homeworks and labs in this class, we wanted each person to learn how to do each thing, right? I didn't want you to go through the entire class without ever learning how to use an oscilloscope. For the project in groups of 3, it is fine to divide and assign tasks, right? That makes sense for a competition like this. But somebody still has to write the code, right? So if you are 3 mechies all just itching for an excuse to go use the RPL in the machine shop, somebody still has to write the code for the robot. So if you have 3 friends who are like, oh, we all want to do this for each other, then don't have that like, oh shit, nobody wants to write the code moment. And okay, I don't want this project to ruin any friendships, right? I want you to, if you're friends going into the project, I want you to be friends coming out of it. So, you know, I don't know how many computer science students we have in here, but you know, if people try and grab the computer science students, like, oh, we can just make them write the code. Again, like I mentioned since the beginning of the semester, even if you're not the one doing a task, you're working on a team, so you should know how it works and what the other people on the team are doing. Especially if someone gets sick or can't be there for the entire competition or a specific day in lab, right? You don't want to have just poorly commented code that nobody else in your group has any idea how it works if they need to change something when you're not there, or some physical mechanism on the robot where something breaks during the competition and you need to pull it off to the side and try and duct tape it back together real quick, right? There's no time to go 3D print more stuff, right? It's just kind of sideline repairs with a screwdriver or whatever you can do just kind of before your next match. So make sure everybody on your team at least knows how everything works, even if they're not a wire comes loose. That's another really good example, right? If these robots are crashing into each other, this is all using a solderless breadboard. There's no soldering. So if your color sensor wires all get yanked out, right, and the person who wired it isn't there, somebody's got to put the wires back in the right spot. Okay, so I'm announcing this now so you can start thinking about it. You kind of have the week and the weekend to mull over it. And again, my goal is to have the spreadsheet for signups live on Monday, so you can sign up before break and then again start doing the EdPost stuff. Any questions on that whole thing? Yes?
Do the groups have to be in your lab section?
No, so that is, I'm glad you asked that now. We're going to go over all of this next week. After spring break, we switched to what we call an open lab format, where there is just going to be a sign-up sheet with multiple slots for every week. So beyond, we have 10 scheduled sections now, there will be additional sections scheduled in the evening. Not identical to the current office hours schedule, but kind of similar, where now maybe there will be more like 4 or 5 2-hour chunks per day, as opposed to just 2. Because after spring break, it's full robot project. There's no more homework, there's no more regular labs. It's just you should plan on pretty much all your out of lecture time in this course is going to be spent on the project. Each team will get a bin with all the robot parts in it. You can take that bin home, back to your dorm or whatever, to work on the robot, but some of the facilities you need, like the physical plywood competition boards and the little wooden cubes and everything, will only be available in the lab. So you shouldn't plan on just being able to do this at home. And that's another thing to consider when forming teams. You want to make sure you don't have completely different schedules. You're going to need some overlap where ideally all 3 of you can meet in the same room at the same time. So if you're on Monday and you want to team up with somebody from Tuesday and Wednesday, that's fine, but you'll all need to make sure you have some evening or afternoon availability where you can all meet. Yes?
Is it for non-mechie people that it might be kind of hard to like ask people around if they're in the team or not? Would there be like a specific system where like you could like put in your name and stuff?
Okay. Were you here at the very beginning when I talked about doing this in our discussion?
Yes.
Okay. So the question was for the non-mechies who want to, basically Ed Discussion is that platform, right? If you're just, you can make a public post that just says, hey, I don't know anyone, I'm at your BME, right? You know, I'm BME, if somebody is a team of 2 and you know, you're looking for someone, I'm happy to join. And then if that doesn't work out, then we will still assign the kind of people who don't manage to be on a team. But we, you know, there's the different tags on Ed Discussions, so homework, labs, project. I guess I could create a 5th one specifically for teams, so it's separate from more like tactical questions about the project. I'm actually going to jot that down for myself. So that would be the way to kind of get in touch with other students and figure out how to do that. Okay? And again, we are probably Monday next week, I'm going to devote an entire class period to going all over all of the other rules and logistics for the competition, so you don't have to worry about that just yet, but you can at least start thinking about team formation. Okay, other questions on the team stuff? Okay, I wanted to talk about that first. I'm going to deactivate this poll because it's been up, I guess, 10 seconds in case you got here and didn't respond to it yet. 10, 5, 4, 3, 2, 1. Deactivate. Okay. I am curious. I'm not going to make the results of this one public. This is just for my sake. How hard everybody thinks the exam was, and maybe correlated with how much you hate me now if you did it before. So on a scale of 1 to 5, where 1 is very easy, 5 is very hard, and 3 is average, meaning comparable to other junior level MAE exams. So not physics department or your electives or whatever, kind of using junior level, so fluids and solids from the fall, heat transfer this spring. I guess if you're, and again, if you're not a MAE, average relative to your department, or if you're a senior, average relative to what you remember the junior level exams being like. All right, 15 seconds to make your mind up and reply to that. 10, 5, 4, 3, 2, 1. Deactivate. Quick. Okay, so that is a pretty good normal distribution around average, if anything skewing a little on the easy side. So hopefully I was not way off target. Okay, again, that was just kind of for my sake comparing this exam to previous years. All right. Can you guys hear me? The light on this mic is red instead of green. Is it on? Okay. I don't know if that means the battery's low or something. If this cuts out, let me know because I won't notice. Okay. All right. That is it for initial logistics stuff. We are going to switch now. We're going to start out paper and pencil and hopefully get to Tinkercad before the lecture ends, but it kind of depends on how long this initial part takes. New microcontroller topic, timers. Okay, this is going to be a new set of registers we haven't learned about yet, and a new microcontroller functionality we haven't learned about yet. The motivation for this is, I know we have back-to-back labs, so a lot of you are still thinking about lab 3. We have lab 4 next week, where you are going to learn to use the color sensor, which you need for the robot competition to know which side of the board you're on. Remember, we have these colored yellow and blue competition boards. That color sensor, this is kind of going to be a high-level overview of how it works, and then there's more details about it in the lab 4 pre-lab. So this is my cartoon drawing of the color sensor, kind of a side view. Okay, that color sensor has LEDs that emit white light, and a photodetector that's going to detect how much of that light is reflected from a surface, okay, which on its own doesn't really tell you much about color, but it has selectable filters to filter different colors of light. So if you emit white light and have the red filter on, okay, then that filter is mostly only going to let red light through, okay, and filter out other colors of light, right? So if I shine that light at a red surface, I'm going to get a lot of red light reflected back, right? But if I shine it at a blue surface, blue absorbs red wavelengths, so I'm not going to get much red light reflected back, okay? So it has red, green, and I'm not going to write all of this down now because it's all in the lab, but it has red, green, and blue filters, and by selecting a filter, and measuring the amount of reflected light, you can figure out, okay, what color am I looking at? Right? If I see a lot of reflected red light, then I'm probably looking at red. So it's not just a magic, you point at it and it just tells you, oh, this is blue, purple, green, whatever. You have to kind of calibrate it and correlate how much light is being reflected and figure out what color that means you're seeing. The output of the sensor is a square wave where frequency is important. So where the frequency of the square wave is proportional to the light intensity, or the amount of reflected light. Okay, so if it's a really high frequency, like that, that means it's measuring more light. If it's a lower frequency like that, that means it's measuring less light. Okay, so I have a square wave. That means it's a digital signal that can only be high or low. Okay, we've seen the Arduino I/O pins function as digital pins. But to measure that frequency, we need to measure the time of one of these pulses. Okay, so technically the period would be from here to here, and then the frequency would be 1 over the period, right? So there's the period, and then the frequency in hertz with no stupid factors of 2 pi this time is just 1 over the period in seconds. We want to measure either the period or the frequency so we can use that to calibrate the sensor. Okay. If we were using the Arduino language, which you're not allowed to do in this class, there's a super convenient command just called pulse in that does that. It just measures the duration of a pulse, of a high pulse like this, in milliseconds. You're not allowed to do that because it's too easy. So we are going to piece together something we already know with something new we're going to learn today. Okay, we already know interrupts, right? We already know that if we have a rising or falling edge, we have 2 different options for an interrupt that can detect that and trigger an interrupt service routine in the code. Okay, we learned about pin change interrupts and external interrupts. You use them both on homework 6. There are some slight differences between them, but basically they can both do the same thing, detect this rising or falling edge. Okay. The new thing is that now we need to measure the elapsed time between these interrupts. Okay, I need to know how long once this one fires, how long did it take until the next one fired? And to do that, I need something called a timer, which is exactly like it sounds, kind of just like a stopwatch. It's something where I can say, hit start. Okay, it starts at 0, I'm going to start the timer, la la la, I'm going to wait, okay, I have another interrupt, I'm going to stop my stopwatch and get the value and figure out what that period was. Okay, conceptually that's what we're going to do. And there are going to be lots of other uses for timers that we'll get to over the next few lectures, but this is kind of the first priority because this is what you have to do in Lab 4. Okay, conceptual questions about any of that so far? Okay, so thinking of the stopwatch example. Okay, say I have just a good old-fashioned stopwatch, or like the stopwatch app on your phone, right? It might look something like this, where it's hours, 2 digits per minute, and then 2 digits in a decimal for seconds, or something, right? And then depending on the number of digits in the watch, if you just hit start, eventually it's going to count up to something like 9 hours, 59 minutes, and 59.9 seconds, and that's the biggest value the timer can hold, right? You're out of digits in your clock. Okay, so once it hits that, it's going to wrap back around to 0. Okay, now this is in hours, minutes, and seconds. Right, but if I was just counting seconds and I only had a certain number of digits, it would work the same way, right? If I had, I don't know, 5 digits and I started at 0 seconds, then I could count up to 99,999 seconds, but I don't have 6 digits, I can't go up to 100,000, so I'm just going to wrap back around to 0. Okay, everybody with me so far? Okay, timers in the microcontroller are going to work the same way, except the timer value is stored in a binary register. Okay, so it's going to start at 0B, 1, 2, 3, 4, 5, 6, 7, 8 zeros for an 8-bit. We're going to talk later this lecture about how there's also 16-bit timers, so 16 whole zeros that I'm not going to bother writing out right now. And it's going to count up to 0B, 1, 2, 3, 4, 5, 6, 7, 8. And then it's going to wrap back around, okay? If I only have 8 bits, that is the biggest number I can store, 200, that equivalent to decimal 255. Okay, you can go back to the notes about how binary numbers work, okay? Start doesn't go up to 256 because we start at 0. Okay, so for an 8-bit timer, I can basically count from 0 to 255 and then wrap back around. Okay, but same concept for all of these. There's just a limit to how many digits I can store. Once I hit whatever the max is, I'm going to overflow or wrap back around to 0. I use the words overflow and wrap around somewhat interchangeably, but technically it's called overflow. And this also ties back into, I forget which lecture, where we really briefly talked about variable types in C, and some only have a certain number of bits, and they all only have a certain number of bits that they can store, right? So if I have some variable x that's an 8-bit integer, and I write x equals 255, and then on my next line of code I write x equals x plus 1, x isn't going to be 256, because I don't have enough bits. X is going to become 0. So that can be a source of weird errors in your code, depending on what you're doing. If you have some variable and you're incrementing it, and you don't remember that, oh, it was only an 8-bit integer or a 16-bit integer, and you exceed the max value and look at, like, why is that value 0, or why is it only 2 or 3? It should be bigger. It's because it overflowed. Okay, so that idea is not unique to timers. That applies to any register. Okay. And if you're confused, stop me now, because we're going to keep going on the timer stuff. Okay? All right, we are going to move over to a new piece of paper, because this one's going to get a little crowded. All right. So specific to the ATmega 328P, again, the microcontroller that the Arduino is based on, it has what is called a system clock that operates at 16 megahertz, right? So that is kind of slow as far as modern computer processors go, right? Those are in the gigahertz, but this is a very cheap, very low power, over 10-year-old microcontroller, right? So this is not anywhere near the kind of power or speed of your desktop computer, but for stuff the Arduino is doing, that doesn't really matter. That clock is an internal square wave. Okay, so this is the system clock. It's just this internal signal that's generated so the rest of the microcontroller can use it for timing purposes. Okay? And the period of that square wave, t, is 1 over f. So if you take 1 over 16 times 10 to the 6th hertz, you get 62.5 nanoseconds for one period or one clock tick. Okay, so when we talk about, we say a clock tick of the microcontroller, that doesn't mean 1 second. Okay, like a tick of that clock is 1 second, but we're not using a wall clock or your wristwatch or app on your phone, right? We're using the microcontroller's internal clock, where a single clock tick is 1 second. Okay? So if we look at a graph of a timer value, okay, if we start the timer and put clock ticks on the x-axis, so 1, 0, 2, 3, 4, 5, and then up here is the timer value. I'm going to draw this in a different color. The timer value increments once on each clock tick. Okay, so the timer is going to start out at 0, and then after 1 clock tick, it's going to go up to 1, After another clock tick, it's going to go up to 2. Another clock tick, it's going to go up to 3, and so on. So if we zoom in really far, it kind of looks like this staircase function, right? Where the timer value is constant for each clock tick. Okay, if we zoom out far enough, so this is the same graph, and again, this is specifically for an 8-bit timer here. If we zoom out far enough, okay, we zoom out far enough so we can't really see the jaggedness of that edge, right? We just see the timer value counting up linearly, but then it's going to hit this maximum value for an 8-bit register. Remember, it can't keep going. It can't be more than 255. So it's going to overflow back down to 0. And keep doing this. It'll start up, count up again, go back down to 0. So if we zoom out, it kind of looks like a sawtooth wave. If you zoom in, you can kind of see the staircase or step function, whatever you want to call it. Okay, so that is just taking that idea of, again, I'm going from 0 up to 255, and then wrapping around. That's just taking that idea and graphing it with clock ticks on the x-axis. Okay, if I want that x-axis to be in time, then I need to multiply the clock ticks by that 62.5 nanoseconds, right? So that first tick would be 62.5 nanoseconds. Next one would be 125 nanoseconds. Next one would be 187.5 nanoseconds, and so on. Okay, so it's important not to get those two different units or systems mixed up. Okay? Questions on that? All right, I see people writing, so I'm going to leave that there for a minute before I keep going. I'm going to try and I can't really keep that. So, now the ATmega 328P only has 8 and 16-bit timers, but to illustrate this a little better, we're going to talk about an imaginary 2-bit timer, okay? Because this is kind of simpler to draw and talk about. So say we have this 2-bit timer. Okay, so in decimal, that timer can just count 0, 1, 2, 3, and then it overflows. In binary, that means it can go 0B, 0, 0, 0B, 0, 1, 0B, 1, 0, 0B, 1, 1, and then overflow. Okay, so 0B, 1, 1 is decimal 3, and so on. So if we look at this graph again, with the clock ticks, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 1, 2, 3. Okay. Timer value starts at 0, goes up to 1, goes up to 2, goes up to 3. 3 is the maximum value it can store. Okay, so then it goes back down. Okay. 1, 2, 3, like that, and then it goes back down. Okay, so the overflow period or how long it takes for that timer to wrap around or overflow, that is equal 2 to the n clock ticks for an n-bit timer. This is a 2-bit timer. But the max value, right, this only goes up to 3, it doesn't go up to 4. Okay, the max value is equal to 2 to the n minus 1 for an n-bit timer. Okay, so it's important not to forget that minus 1. There's a difference between looking at the max value and the actual overflow period. Okay, and if you want to calculate this overflow period, so that was in clock ticks. If you want to know it in seconds, then that's going to be 2 to the n times t, where t is the period of 1 clock tick. Which is 62.5 nanoseconds for the AT Mega 328V. Okay. Given that, I'm going to launch a poll everywhere that I want you to do the calculation, but not actually answer the question. Okay. How long does it take for the 8-bit timer to overflow in seconds? Okay. So this was for an imaginary 2-bit timer. How long does it? Remember, don't actually answer the question. Okay. How long does it take for don't actually answer the question, I mean don't actually respond to the poll everywhere, but do the calculation. Okay, and then we'll just do kind of a show of hands. How long does it take the 8-bit timer to overflow? In seconds, not clock ticks. Okay, remember, if you are here, do not answer this question. If you have already answered it, delete your answer. Okay, I'm just going to go through the poll EV answers, and you can raise your hand for it. Again, remember, if you're here, do not answer this question. Delete your answer if you answered it. 255 microseconds. Raise your hand if you agree with the answer. 256 microseconds. Okay. 15.9375 microseconds. 16 microseconds. Sorry, Rob. None of the above. Okay, correct answer is 16 microseconds, so Rob, you forgot to multiply by the period. Right? Okay, so again, be careful with the clock ticks versus nanoseconds unit conversion. So how long does it take the 8-bit timer to overflow? That's 2 to the 8. There's no -1. We're asking about the overflow period, not the max value. And then times the 62.5 nanoseconds. That'll give you 16,000 nanoseconds or 16 microseconds. Okay, so in human time, that is really fast, right? 16 microseconds before the thing overflows. In microcontroller time or computer time, that's not that fast, right? A computer can do a lot in that amount of time. But sometimes you might still want to slow the timer down. Okay, say, hey, you're going too fast. I don't actually need to measure things at a resolution of 62.5 nanoseconds, so it is okay to increment slower. Like imagine if you could make your stopwatch only count up every 10, only increase the second counter every 10 seconds instead of every second. Okay? We can do that with something called a prescaler with the timer, which slows the timer down by a factor of n, and there are only, we'll see when we get to the registers, there are only certain values available for the prescaler. You can't just pick any number you want. So 1, 8, 64, 256, and 10, 24. I'm going to write down double check data sheet, because that is not necessarily universally true for all microcontrollers or all timers. I'm 99% sure I drew those down right, but I don't know if there's a 128 missing here. I need to double check the data sheet. So this lets you take the timer and say, okay, rather than ticking up on every clock tick like this, I'm only going to increment once every 8 clock ticks. So it looks like, again, I'm not drawing that perfectly to scale. All right, so there's n equals 1, or just normal timer operation where it's every clock tick. Here's n equals 8, where I've slowed the timer down by a factor of 8. Okay, so that is going to lead to our next poll everywhere question, which I do actually want you to answer. Again, I didn't deactivate this one here yet, so if you're here, this is your last chance to delete your answer for this one. 5, 4, 3, 2, 1. Deactivate. Okay. Next one. How long does it take the 16-bit timer to overflow if the prescaler is set to 1024? Okay. 16-bit to how long for 16-bit timer to overflow if the prescaler is set to 1024? Okay, so we now have a 16-bit timer instead of an 8-bit timer. And instead of the prescaler being 1, we have the prescaler set to 1024. So we have slowed things down by a factor of 1024. All right, let's give it another 30 seconds for that. We have most of the replies in. Okay, 15, 10, 5, 4, 3, 2, 1, deactivate. Okay, 66% of you got the correct answer, which was 4.194304 seconds. Looks like a handful of you were off on the calculation, so I will show that real quick here. So again, for the prescaler of 1, okay, we have the overflow period equals just 2 to the 16th times the 62.5 nanoseconds. Okay, that's the equation I wrote down in the last slide there. But now we need to multiply that by the prescaler too, because again, we are slowing the timer down. So I'm only counting up every 1024th clock tick instead of every clock tick. So when you multiply that by 1024 and convert to seconds instead of nanoseconds, then you should get 4.194. Yes. 304 seconds. Okay, so that's a little more reasonable amount of time on a human scale if you're thinking about something like pushing a button, right? Or you want to measure something that takes a couple seconds. Now, why is this important? Why do I care what the max overflow period is? Going back to what we talked about with the color sensor, you have, so this is the color sensor output. Okay, and you want to measure this period, okay, which is not the same as the clock tick period or the period it takes the timer to overflow. Okay, so ideally, what I want to do, if this is my timer, I want to, let me slide this up, sorry. I want to fire an interrupt here, start my timer, so my timer's counting up as I'm waiting for that next interrupt, fire another interrupt here, and get my timer value. Okay? Get. But that timer value is stored in a register that's measuring clock ticks, or some multiple of clock ticks depending on the prescaler, right? It's not in seconds, so then you're going to need to convert it to seconds. Now, what could the problem be if my timer overflows before my second interrupt fires? Can anyone tell me why that would be a bad thing?
You can't actually measure time between, like accurately measure time between each of the like rising edges.
Correct. Okay, so if my timer overflows too soon, say if my timer looks like this, oops, I hit the overflow point, and I do that, right? I can still fire an interrupt and grab the timer value at the end, but the time is going to be wrong. Okay, I've only measured now the elapsed time from the last time the timer reset to there, as opposed to the actual time between the two interrupts. Okay, so I'm not going to do it for you now, but part of pre-lab 4 is going to be asking you to figure out, okay, what prescaler should I use? You're going to have an expected range. Actually, I forget if this is for pre-lab 4 or during the actual lab. You will initially just use the oscilloscope to measure the color sensor output, so you will have an idea of what this frequency range and period range should be. And then you can figure out, okay, based on the maximum possible period that I could ever expect to measure for the color sensor, what is the minimum prescaler value I need for the timer? I want to make sure that my timer, it's going to overflow eventually, right? You can't stop it from overflowing, but I want to make sure that my timer isn't going to overflow until well after I would expect this second interrupt to fire. Okay, because if it overflows too early, it's going to mess up your color sensor reading. Okay, so all of that is the motivation setting up for what we're going to do in lab 4. Now, we haven't actually talked about any registers yet. Okay, so to do all of this, to both get the timer value and to turn the timer on, we need to use registers. Okay, and I think we're not actually going to have time to get to Tinkercad today, but I'm going to talk about the registers so we can jump right into using Tinkercad on Friday. Okay, again, think of registers, they are physical locations in the microcontroller's memory, but there are different types of registers that have different functions. Okay, so we have learned about the I/O registers, so DDR, port, and pin, that set pins as inputs or outputs, and then either set the outputs high or low or read the inputs. We learned about a handful of different registers that control the interrupts. Okay, think of them like control switches or settings that let you kind of turn different special functions in the microcontroller on or off. Same thing with timers. There are going to be some new registers. These ones are a little scarier. They are big and have lots of different bits in them, but we're going to take it slowly with the time we have left today to kind of set this up, and then we'll jump into using them in Tinkercad on Friday. Okay, so I'm going to get a new piece of paper to write this down. Now, the registers we're going to talk about here are specific to timer 1. Okay, I should have mentioned so far that the ATmega 328P actually has 3 timers, and for whatever reason, timer 1 is the 16-bit one, and timer 0 and 2 are 8-bit. So everything we're going to talk about here is specific to timer 1. Timers 0 and 2 are conceptually similar, but they have different registers in the data sheet. So if you, and we'll get more to this in lecture next week and after spring break, when you use multiple timers for different things in your robot, you have to go look up the right registers for the timer you're using. Okay, I'm going to write down a whole bunch of stuff here and then label it, so give me 1 second. So the TCCR1A register, so that stands for Timer Control Something Register 1A. I don't remember exactly what the acronym is, but Timer Control Register It has 8 bits. COM1A1, COM1A0, COM1B1, COM1B0, and there's 2 blank ones we don't care about. And then there's WGM11, WGM10. Okay, so rather than just pulling up the data sheet, this is all in the data sheet, but rather than pulling up the PDF, I'm writing it down here so I can annotate it, and you can have a single page telling you what these different bits do. Okay? There's a second timer control register, TCCR2A, that also has 8 bits, ICNC1, ICES1, one with no name, WGM13, WGM12, CS12, CS11, CS10. Okay, 2 registers, 16 bits total, 3 of which actually don't have names and don't do anything. Okay, so when we write Tinkercad code on Friday, we are going to be setting these bits based on what we want the timer to do. Okay, labeling these batches of bits. The WGM bits, that stands for waveform generation mode. Okay, there's going to be a table in the datasheet that gives you different options for what the timer can do. Again, we haven't really started to talk about those different options yet, but these bits are going to let you select different modes of operation for the timer. Okay. The CS bits stand for clock select, and that's how you pick the prescaler. Okay, we talked about how there's different n equals 1, 8, 64. Whatever, there's a table in the data sheet that tells you, okay, if I want to pick a prescaler of 1024, what do I set those bits to? Okay. These 2, to be honest, I don't even know what they do. We are not using them in this class, so you don't need to worry about them. I'd have to read the data sheet to see what they do. Not used in this class. And these 4, the COM bits, are related to something called PWM, pulse width modulation, which I think I had mentioned earlier this semester. It's how we are going to control the speed of a motor if you want to. So you can just make your robot drive full speed all the time. That may or may not be a good idea. It might make it a little easier to kind of accidentally drive over the edge if you're going too fast. Or if you want to control a servo motor for some mechanism that you're building for your robot to collect the cubes or something, that's how we're going to use those guys, but you're not going to need them for lab 4. So it's pretty much going to be lab 4. You're going to need to know what these waveform generation mode and clock select bits do. And again, all of that is just going to be to enable us to do this. Okay, how do we start the timer, and then how do we get the value of the timer? All right, let me see if there's anything else I want to talk about real quick here. Okay, now we only have 2 minutes left, and since we don't have time to pull Tinkercad out today, actually 1 minute left. It's nice out. I'm going to go meet my wife at the dairy bar for ice cream. You guys should, I don't know, do the same. And hopefully the exam was not too brutal. I will try to have the TAs turn around grading on that within 1 week. As usual, I'll be here for questions. Thank you.